This is Math 432, Applied Combinatorics. I'm Professor Asaph, and we're going to be talking in this series about Pascal's Triangle and properties of the binomial coefficients that we can discern from it. So here is Pascal's Triangle. The way that this is generated is to figure out what this value here should be. We work from the top down, so we'll take the two numbers that are above it, add them together, and that's what will produce this number. If there aren't two numbers above a given number, then you're at the edge, and the edge cases are always 1. So that's Pascal's triangle and how we generate it. It's made by combining two terms above, and that really is telling us something about binomial coefficients due to the following theorem, which is the kth entry in row R Pascal's triangle is the binomial coefficient, row n maybe, is the binomial coefficient in choose k. So for this to work out, we need to count this as the 0th row. This, everything on this the 0th entry. This is the first entry. This is the second entry. So you can see here that this number 6 is the second entry in the 4th row, which is good because 4 choose 2 is 6. Okay, so how do we see this? How do we know that this generates Pascal's triangle generates the binomial coefficients? Well, it's actually due to the following theorem, which is the one that I'll really prove, and then you can deduce the theorem above it from this. Pascal's recurrence says the following. So this is due to Pascal. Maybe he wasn't the first to notice it. I'm not really sure. Pascal's recurrence, it states that n choose k plus n choose k plus 1 is equal to n plus 1 choose k plus 1. It's called Pascal's recurrence because it's exactly telling us what this sequence is. So here we had the example of 4 choose 1 plus 4 choose 2 is equal to 5 choose 2. That's what the highlighted example is over here on the right. So it's telling us that this algorithm by which we generate this Pascal's triangle is the same algorithm satisfied by the binomial coefficients. And then once we check our initial conditions and see that they are indeed the same, that 0 choose 0 is 1, there's one way to do nothing, then we indeed get Pascal's triangle giving us the binomial coefficients. So let's prove this recurrence relation. Of course, we can prove it algebraically. That's a rather uninspired proof. Let's try to do it in a more inspired way, which means more combinatorial way. So what does the right-hand side tell us? Well, we know that n plus 1 choose k plus 1. By definition, this is the number of k plus 1 element subsets of the numbers 1, 2, up to n plus 1. Okay? Now, what's the left-hand side tell us? So the left-hand side is a little more interesting. We have two things going on. So we've got, on the one hand, we have n choose k, which is the number of k element subsets of the numbers 1 up to n. And then we also have, we're adding to this amount, n choose k plus 1, which is the number of k plus 1 element subsets of the numbers 1 up to n. So what you can do if you want to come up with a combinatorial proof is write down what these things mean, right? Write down all your ingredients and then think about how they relate, okay? Here we have elements up to n plus 1, and here they're only up to n. So how could we think about mapping these guys down to these guys in some kind of bijective fashion? And that's really the key here. So we're going to think about S as a subset of the numbers 1, 2, all the way up to n plus 1. And we're going to have the size of S be k plus 1. Okay, that way it's one of these objects that's counted on the top. And what we're going to do is think about two different ways to map it. We're going to map it down to this guy or this guy based on some condition, some disjoint condition. And now, in this case, on the left, we know that we need to lose one element. So let's do this if n plus 1 is an element of S. We're going to take it out. So then we're going to get S minus n plus 1. That will then be a subset of the numbers just 1 up to n, and it's of size 1 smaller, which means it's size k. And the flip side, the everything else condition, would be if n plus 1 is not an element of S. Then I'm still going to have the same number of elements and the same elements, but since I didn't have n plus 1, I'm a subset of the numbers 1 up to n. So that means that I've created a bijection between the things counted on top and the things counted on bottom, using the idea that these are disjoint. And disjoint sets is going to be an important topic that we're going to discuss soon, so it's kind of a nice, refreshing way to work at this. I will point out that you could do a brute force proof. If you just expand out the fact that n choose k is equal to, let's go all the way into factorials, n factorial, k factorial, n minus k factorial. If you expand out both of these terms and you get a common denominator, okay, then you're going to end up with this term. So if you want, you can give yourself an algebraic proof, but it's kind of nice to keep these combinatorial proofs in mind. And next we'll look at some other properties that we notice when we look at rows of Pascal's triangle.